meters. And so with moving coil meters, we are talking about the ammeter, to the voltmeter, and 3 galvanometer. The ammeter capital A, voltmeter capital V, and this is capital G. These are what we call the moving coil meters. These are instruments that operate on the principle of electromagnetic induction. Yesterday I explained to you what electromagnetic induction is. When we talk about electromagnetism, we have electromagnetic induction, which we would also talk about, and electromagnetism. Electromagnetism is a principle of making an artificial magnet using electricity. So the process of making magnets using electricity or electrical energy. So we are making magnetism out of electricity, hence electro coming from electrical magnetism. So it's more or less like artificial way of making magnets. Okay, artificial way of making magnets. Magnets, we have permanent magnets, we have temporal magnets. The permanent magnets are the magnets we use in the lab most often, magnets used by tailors to, attract pieces of pins, that they are pins, and then blades and all that. These are permanent magnets because a bar magnet is like this, whether cylindrical or curved magnets, they are all permanent magnets. Okay, they are termed permanent because the magnetic field is always there, or its magnetic strength is always on. When you pick a bar magnet, a permanent one, of course, this is a bar magnet. The region around the magnet where magnetic effect can be felt is what we call the magnetic field. So the magnetic field is the region or area around a bar magnet where magnetic effects can be felt. So with permanent magnets, this is how the field looks like. The magnetic field lines, which are what I've drawn around, originate from the north and always terminates or enters the south. So the arrow must point out from the north and must point in to the South Pole. These lines are what we call as magnetic field lines. So for a permanent magnet, the magnetic field is always on. 2, the poles, okay, is always permanent, can never be interchanged. If this is the North Pole and this is the South Pole, so long as this remains magnetized, we cannot change the poles. This will continue to be North forever. This will continue to be South forever. And this on, so long as you are not demagnetizing it by heating the bar magnet or hammering it, the magnetic effect will always be on. If it's a curved magnet, and this is the North, this will be South, then this thing, the magnetic field lines, the poles will always be there. The reason for which we call the bar magnet as magnetic field, a permanent magnet. In some other applications of magnetism, we will need magnetic effects as at when we need it. So we don't expect it to be always on. When we need it, we on it. When we don't need it, we off it. The reason for which we will need a temporal magnet. And it has a lot of applications which we'll talk about. So for temporal magnets, we want to artificially create, even though this is not God made, this is Abia made, Mr. Abia made. But because this is permanent, we want to create another one whose magnetic field can be controlled. When we need it, we on it. When we don't need it, we off it. We can also flip or change the poles. The reason for electromagnetism. So, how do we make electromagnets? If we pick a conductor, a wire, and we pass current through it, there is magnetic field created around a current carrying conductor. So there is a magnetic field created around, let me put it into very good words or sentence for you to write. So how do we make electromagnets? A current carrying conductor always has magnetic field around it. So the moment you have a wire, aka a conductor, and you pass current through the conductor, okay, there is magnetic field created around the current carrying conductor. So let's demonstrate, if there's the direction of this, the straight line, vertical straight line is the wire or conductor. The arrow indicates the direction of the current. By Maxwell's corkscrew method, the direction of the magnetic field around the conductor can be determined using the right hand. Then this is also known as the grip rule. Grip rule. So we can use Maxwell's corkscrew or the grip rule to determine the direction of magnetic field around a current carrying conductor. And I'm demonstrating that to you quickly. Hold, assuming the marker is a conductor. Hold it, let your thumb represent the direction of the current. So if the current is going up, grip the conductor or the marker and let your thumb represent the direction of the current within the wire. Your 4 other fingers indicate the direction of the magnetic field around the conductor. So if you look at my fingers, my 4 fingers point outside the board. Okay, outside. Please practice it. So this is the direction of the current. Okay, the conductor is the marker. It is well gripped. My 4 other fingers represent the direction of the current in the conductor, and it is pointing towards you or away from the board. So if I want to draw the magnetic field, I draw concentric lines. So my 4 fingers point to you. So the field, the direction of the magnetic field is this. Practice it. So grip the conductor, let your thumb represent the direction of the current, and the 4 fingers will point to the direction of the magnetic field. If the current is also going inside that or downward, hold the conductor or grip it, let your thumb represent the direction, and this time it is the direction of the current is downwards. Downwards. So the same method, grip the conductor, let your thumb represent the direction of the current. And my 4 fingers also point to you, but this time in this direction. Okay, away. So it is, if this side is coming this way, then this side goes the opposite way. So this is the magnetic field around a current carrying conductor. Here the current is moving upward. Okay, and here the current is moving in downwards. Please, are we okay? Are we fine?
Yes, sir.
All right, so a current carrying conductor always has a magnetic field around it, and this is how to demonstrate the direct. If the direction of the current is also towards inside the board, I'll point my finger this way to the direction of the board, and it will the field. Okay, the field will look like this. If the direction of the current is coming outside the board, my fingers must be pointed to your direction, and the field will go this way. Okay. All right, so a current carrying conductor has a magnetic field around it. Okay, has a magnetic field around it. So it means the moment you pass a conductor, a current through a conductor, you create a magnetic field. Now, if you want to concentrate the magnetic field around the conductor, we say that you wound the wire conductor to form a coil, which we call as solenoid. So, because if I wound the wire, I form a solenoid. Now I connect an external field, EMF, to the wire. And if you attended a good JHS, like my village JHS. We conducted this simple experiment, okay, where a wire was wounded. Then we connected it to a battery, positive and negative. And we realized that when you push in a nail, this attracts it. There is attraction by this, meaning we formed a magnet. So the moment you connect the coil, which we call solenoid, to the battery, magnetic field is created within it. We've created artificial magnets. And that is electromagnetism. Now, this artificial magnet created is known as a temporal magnet. And this is a temporal magnet because you can always on and off the magnetic field around it. So if you create a key or switch within, this is a switch. Whenever you on it, you on the magnetic field. Whenever you open the key, you off it. So the difference is that this one, we are controlling the magnetic field. We can always on and off the magnetic field. The second advantage of this is that over here, the polarity is always fixed. North would always be north, south would always be south. Here, we can change it. You can change as it stands. If you on it, this side, the positive side becomes the north pole, this side becomes the south pole. The other advantage here is that I can flip or switch the polarity. Make this as south, make this as north. All that I need to do is to change the polarity of the source. Make this negative, and then make this positive. And the polarity will also change. This side becomes south, this side becomes north. So for a temporal magnet, we can always flip its polarity or its poles can be flipped. An added advantage over this one. And because of these features of this magnet, we say this is a temporal magnet. So artificial electromagnetics or electromagnets are temporal magnets. This one, if I want to increase the magnetism, I cannot do anything about it. Its magnetic strength would always be the same as it is designed. Over here, I can increase or decrease its magnetic field. All that I do to either increase or decrease the magnetic field is that maybe if this is a battery with an EMF of 3 volts, increase it to 9 volts. So when you increase the EMF, you increase the current flowing through it. And the magnetic field around can also change. Another way of changing the magnetic field is that increase the number of coils. So by increasing current, you can increase by increasing current, magnetic field can also increase. Two, by increasing the number of coils. So I can increase the magnetic field or the magnetism by increasing the number of coils. What do I mean by number of coils? You see this macaroni thing, macaroni-like, Indomie-like thing. One coil is simply this. So this is one coil, two coils. So as I add a lot of this macaroni thing to it, I'm increasing the coil. So the greater the number of coils, the greater can also be the magnetism. And lastly, we can also increase the magnetic field by increasing the cross-sectional area of the conductor. So by increasing the cross-sectional area of the conductor. So something about electromagnets. Okay. So these are the advantages. All right. As for this, you can't change it. Whatever you are given is what you get. You can't say anything about it. But for temporal magnets, you can always, or electromagnet, you can always change it. So that's the principle on which the ammeter, voltmeter, and galvanometer actually works on. Now, apart from electromagnets, it also works on the principle that if you have a permanent magnet, still an electromagnetism, we haven't moved away from electromagnetism. If you have a permanent magnet, this is a concave shaped bar magnet. When you have a bar magnet and it's shaped like this, it also concentrates the magnetic field. This is north, this is south. So these are permanent magnets, similar to a magnet like this, north, south. But these are concave shaped magnets to retain the magnetic field. I just told you that if you have a bar magnet, the magnetic field lines move from the North Pole and always enters the South Pole. So the field lines originate from the north, terminates into the south, on and on. So if you have this, the same thing, the magnetic field lines will move from the North Pole and enter into the South Pole. This is the magnetic field lines. Now, if you have, these are permanent magnets. When you put a wire that carries current in the vicinity of a permanent magnet, this carries current. The direction of the current is the arrow. So what you see as a vertical arrowed line is a current carrying conductor. So the vertical arrowed line is a current carrying conductor. When you put a current carrying conductor in a field of a permanent magnet, okay, a current carrying conductor placed within the field. Here I mean magnetic field of a permanent magnet. Yes, what happens? Some of you, yes, read a lot. If you place a current carrying conductor within the field of a permanent magnet, class, what happens? What happens? Share your experiences with me. Yes.
Yeah, so the since the current carrying conductor also has a magnetic force around it, it's going to cause a resultant force between the magnetic lines of force and then the magnetic lines of force of the current carrying conductor. Therefore, there's going to be a resultant force which is going to push the current carrying conductor out of the magnetic force, the space in between, sorry.
Field. Okay,
Yes,
so yes, basically that's what you've said. Whenever you put a current carrying conductor in a magnetic field, it experiences a force. So there is a force exerted on the current carrying conductor. So a current carrying conductor placed within the field of a permanent magnet experiences a force. A force F. So there will be a force. It will not be, Gerard, it will not be moved out of the space, but it will be pushed. So if the current carrying conductor is like the marker, you see this in motion, either in this place or this place. It will be in motion, or it will be pushed. And this is because, you see, when you have the current carrying conductor itself is an electromagnet. It's a magnet, temporal magnet. Then the permanent magnet is another magnet. Now, when two magnets come together, they will either attract or repel. So the movement is as a result of either the attraction of the two or repulsion of the two. Okay, so it's because of the resultant force, okay, force of either attraction or force of repulsion between the two. Please, class, are you okay?
Mr. Idris, please, can you take it again?
So what I'm saying is that a current carrying conductor experiences a force in the field of a permanent magnet. This is because the current carrying conductor carrying conductor is an electromagnet. So it's a magnet, but it's a temporal magnet, electromagnet. And the permanent magnet is in itself another magnet. And when two magnets are put, okay, together, either they attract or they repel. Okay, so because this is an electromagnet, a magnet, and this is also a permanent magnet, when two magnets, okay, are put together, the two magnets can either attract or repel. So the force experienced by the current carrying conductor is as a result of the repulsion or the attraction of the two magnets. Please, are we okay?
Yes, please.
So that is the reason for the force. All right. Now, the magnitude of the force experienced by the current carrying conductor in the field of the permanent magnet also depends on some factors. So, magnitude of force on the current carrying conductor depends on the following. One, hello, let me pick this call and then get back to you. Okay, so the magnitude of the force experienced by the current carrying conductor in the vicinity of the permanent magnet depends on the following. One, F, what is the force? Okay, is directly proportional to the magnitude of the magnetic field. Strength, the strength of the magnets. Strength of the magnetic field. And this is the strength of the magnetic field is represented by the letter capital B. Two, the force experienced by the current carrying conductor also depends on the magnitude of the current. F is also directly proportional to current, the current I through the conductor. Then three, the force experienced is also directly proportional to the length of the conductor, L, length of conductor. And lastly, the magnitude of the force experienced by the conductor is also directly proportional to the sine of the angle between the magnetic field and then the conductor. The sine of the angle theta between the magnetic field, okay, and then the conductor. So these are the factors on which the magnitude of the force on the current carrying conductor depends. One, it depends on the strength of this bar magnet. Two, it depends on the magnitude of the current I flowing through the conductor. 3, it depends on the the length of the conductor. And then finally, it also depends on the sign of the angle between the magnetic field and then the conductor itself. Can I change the camera position and continue? Can I flip it and continue? Or if you have any question, let me know. Okay, no comment. So it means I can flip and continue. So let me clear this part of the board. So if the force carried by a current carrying conductor depends on these factors, then when we put all of them together, we can say that F is directly proportional to B, strength of the magnetic field or the bar magnet. F is directly proportional to I. F is directly proportional to L.
Your mic is not on.
Hello. K. Hello, K. Please, can you hear me?
Yes, please.
Okay, if you can't hear me, then you have to reconnect. Okay, so F is directly proportional to BIL, and F is also directly proportional to sine of the angle between the magnetic field. And here we are talking about this. This is the magnetic field lines. So the angle between the conductor and then the magnetic field is what we are talking about. Now, F is equal to a constant of proportionality times BIL sine theta. When you consider the SI unit of all the values, all the quantities here, we have K to be equal to 1. If you consider the SI unit of every individual here, K is equal to 1. And so you have the formula F is equal to BIL sine theta. So for the force exerted on a current carrying conductor, okay, the force is equal to BIL sine theta. BIL sine theta. Where B is the magnetic field strength, I is the current, L is the length of the conductor, and then sine theta is the sine of the angle between the conductor and then the magnetic field F. Please, any question? So we are doing some aspects of electromagnetism. Now, maximum force, F maximum, is experienced by the conductor, is experienced by the conductor when theta is equal to 90. what we are saying is that if the angle between the magnetic field, this is the current carrying conductor, I. Let me draw one magnetic field line. If the angle between this is 90, then we have maximum force exerted on the conductor. It means the conductor will be pushed so much with a greater force. And when theta is 90, we have F maximum equal to Bell, because theta is 90 and sine 90 is 1. So Bell times 1 is equal to that. So for maximum force on the conductor, theta must be equal to 90 degrees. For maximum force, theta must be equal to 90. Now for minimum force, F minimum, theta must be equal to 0. This is because when theta is 0, the force is 0. So minimum force on the conductor is equal to 0, and that occurs when theta is equal to 0 degree. This is it. If this is the magnetic field, F, the magnetic field F, and then the conductor also lies parallel to the magnetic field. The current carrying conductor, I, lies parallel to the magnetic field. When two lines are parallel, the angle between them is 0. Then the conductor experiences a 0 force. A 0 force. Please, is that okay?
Yes, please.
Yes, sir.
Okay. Any question? And you see, look at this electromagnetic thing we are studying. Application of this electromagnetism is in one. I've made mention of moving coil meters, ammeter, voltmeter, galvanometer. These are all equipment that operates on the principle of electromagnetism. So the moving coil meters applications are very, very important. So let's look at them.
Mr.
and then
Idris, what
move.
did you say?
Applications of the moving coil meters.
Moving.
Where
Okay.
applications of electromagnetism or electromagnetism. All that I've said from start up to this is on electromagnetism. So we are looking at where these are applied, hence applications, right?
Yes.
So applications of Gerard, are you there?
Yes, sir.
Electromagnets or electromagnetism. One, we have the moving coil meters. And when we talk of moving coil meters, we are talking about ammeter, voltmeter, and then galvanometer. 2, electric bell. Electric bell in your homes. 3, electric motor. Motors are devices that convert electrical energy to rotational mechanical energy. Or simply, you can say that motors convert electric energy to mechanical energy. But the mechanical energy is rotational kinetic energy. Okay, so electromagnets are applied in moving coil meters, electric bell, and then electric motor. Electric bell, you see, the operation of it is that when you go to homes that have electric bell, the moment you press on the bell, okay, the circuit is closed. When the circuit is closed, current flows through the circuit. Okay, then within the circuitry or the circuit is like this. There are permanent magnets, and this is a conductor that carries current. So when you go and then you press on a switch, you allow current to flow through the conductor. It becomes electromagnet. Now, when electromagnet is in the proximity of another permanent magnet, the current carrying conductor or the electromagnet experience a force. So that force which will be experienced by the conductor is what, okay, pushes it to hit a metal. So as the force, current flows through it, and then it experiences that force. There's a back and forth push. And then you hear it's ringing. Yeah, me too. That is what is happening. Then in the moving coil meters, you see the galvanometer, ammeter, analog ones. I'm not talking about the digital ones we use in the lab, but the analog ones, when you connect and then you close the circuit, there is a deflection of the pointer. The pointer deflects. The deflection of the pointer tells you that, yes, there's current flow. And there is, once current flows, there is a force on the pointer, the reason for which it deflects. Please, are you with me? So when you
Yes,
see
please.
the pointer at 0, and then after closing the circuit, you see when the circuit is well done, you see this, then it means there is a current flow which is exerting a force on a conductor, the reason for which it's moved. Okay, then electric motor. In electric motor, the conductor is formed like a rectangular shape, something which we call as armature. When the circuit is closed, there is a force of acting this side and then this side of the coil. So it turns like this. Okay, it turns like this. Okay, and motors are found in every device that rotates. So your ceiling fan has a motor, electric motor. Okay, your standing fan has electric motor. Toy cars, your washing machine, your blender, every device that rotates has a motor within, and they all work on the principle of electromagnetism. Please, is that okay?
Yes, please. Yes, please.
All right. Any question? Gerard, ask your question. When you finish, Kay, ask your question. Andre, you also ask your question. Okay, please go ahead.
I'm asking a question. I guess that's
Okay. Pardon?
I'm
Oh,
not
I'm
asking a
listening.
question. I just
Oh, I can't hear you. Gerard, I can't hear you.
said.
Uh-huh. Gerard, I'm listening. All right, so let's look at the moving coil meters. Now, the ammeter is used for measuring maximum current in a circuit. The ammeter is used for measuring current flow in a circuit. And so an ideal ammeter must have very low resistance, almost zero resistance, so that it wouldn't have any opposition and it can always measure a maximum current. So an ideal ammeter must have almost zero resistance or very, very low internal resistance so that it can measure optimum current. Andre, is that okay? Andre. Hey, are they gone? Hello, can you hear me?
Yes.
Yes.
Priscilla, what did I say about ammeter? What did I say about an ammeter?
Instead of this, you said it is a device that is used to measure maximum current, and as it should have low resistance so that there will not be any opposition to the current flow.
So we can have absolute zero resistance, but an ideal ammeter must have almost zero internal resistance. Okay, so that it can always measure. So that it can always measure maximum current, because that's its function. Its function is to measure maximum current. So there shouldn't be any much opposition. If there is no much opposition, then it implies that it can do its work well. If the opposition within is so much, then it cannot function properly, because so an ideal ammeter must have almost zero internal resistance or very low, so it can measure maximum current. And then, are you there? Oh. Now, a voltmeter, on the other hand, a voltmeter is used to measure potential difference or voltage drop. It measures either a potential difference or voltage drop. Now, its nature is also it has an ideal voltmeter. Must have a very high internal resistance. so that it allows no current to flow through it. And last time, I made you understand that this is the reason why in a circuit, a voltmeter is connected in parallel. Because if this is a source of EMF, this is our conductor, and then the voltmeter is connected in series. Connecting in series means that you break the circuit and push the device into it. Is that okay? So that's what, by connecting the voltmeter, that's what you've done. This arrangement means that the voltmeter is in series with the circuit. Now, if this is the situation, the voltmeter will not allow current to pass through because current flows within the volume of the conductor. The charges drift the electrons, free electrons, from atom to atom. So an electron moves from here, comes to this, moves from here on and on and on. And by so doing, electrons move within the conductor. So this is the conductor. So when you connect the voltmeter in series with it, because it has a very high internal resistance, the charges or electrons cannot move past it. So the moment they get here, they can't cross. They can't. So that is why in a circuit, you don't connect a voltmeter in series, okay, within the circuit. Is that okay? We don't connect a voltmeter in series. Now, we connect
Mr.
voltmeter. Hello.
Please, when it gets to the point where the voltmeter is, that you said it cannot pass, can it go back? Like, will it go back?
The current, the charges will not cross. Okay. Current flows from positive to negative, so it's here. It cannot move and close the circuit. So it's as if no current flows through it. That is why in using the voltmeter to measure the EMF, we said determining the EMF of the cell when no current passes through the circuit. So the voltmeter doesn't measure amount current. It only measures potential difference across 2 points. Is that okay? Now, if you have a resistor, maybe a bulb or a load, and you want to measure the potential difference across the bulb, you cannot bring the voltmeter here because the voltmeter will not allow current to pass it. It will end here. And so the moment you connect the voltmeter in series, the bulb will not even light up because it will resist the flow of current, because its nature is that it has a very high internal resistance. So charges will not move past it. In a circuit, voltmeter must always be connected in parallel. And parallel circuit is this. This is the voltmeter connected to a wire, 2 different wires. Then join the wire to the area where the potential difference is to be determined. So if this is, yes, we are looking for the potential difference across, okay, the ball. When I place the wire here and then here, it will measure. When I put it here, so connect it this way, V. Now, when this is a wire connecting to the voltmeter, I told you last time that current flows from the positive. So when the current gets to a junction, in an electrical circuit, a junction is a point where 3 or more wires actually interconnect. So 1, 2, 3, a junction is created here. There's a junction. When the current gets to the junction, it will break into two. I1, I2 by Kirchhoff's law. So because this has a very high internal resistance, a greater part of the current would go here, will pass through the ball. Now that little component, when it gets here, because it cannot move past it, it will come back and then use this route. So this will still have no effect on the current flow because there is an alternative route for it to pass. And current always flows through a point where the resistance is very, very low. Current always flows through a point where resistance is very, very low. So if you are offering a very high resistance, I will not use this route, but we use this route and still flow. The reason for which voltmeter must be connected in parallel. Gerard, ask your question.
Stadium, please, I'm writing the.
Okay, ask your question. Andrew, is that a question?
No, please.
Okay, all right. So today we'll even close at 3:30. So you
Okay.
can go, okay?
Okay.
Because I'm looking at tomorrow as well. So you
Okay.
all right. So that is the nature of a voltmeter. Ammeter is always connected in series because its purpose is to measure current flow. And so when you break the circuit and you put it in, yes, current can freely go because an ammeter has a very low internal resistance. So it wouldn't be a nuisance to the current flow. Galvanometer. A galvanometer is an instrument that is used to measure small amount of current, small voltage drop or potential difference. So a galvanometer is a dual instrument. It measures small amount of current or small amount of voltage drop or potential difference. Potential difference or voltage drop. It is also used to show the directional flow of current. So what it means is that it shows the directional flow of current. Maybe current is flowing from my left to right. So when you put in a galvanometer, it will flip this way to show you that this current is moving from left to right. Maybe current is flowing from right to left. So when you put in a galvanometer, it flips this way to show you that, or indicate that the current is moving from right to left. Okay, so its function is to measure small amounts of current and small amount of potential difference across 2 points, and also to indicate the directional flow of current. Now, the characteristics of a galvanometer is such that it has a very high internal resistance. A galvanometer has a very high internal resistance. Its voltage and then current range is usually in terms of micro or milliamps and volts. So we are talking about it's being used to measure small amounts of current, meaning the current range a galvanometer can measure is usually in microamps and milliamps. Very, very small. Meaning you can't even use this to measure 0.5 ampere because its range is in micro and milli. And micro is 10 to the power -6 ampere. 0.00001234. This is what we are talking about. Or if it's in milliamps, we are talking about 0.001 ampere. It isn't anything close to 0.5. And that's the calibration of galvanometers. If it's in for measuring current, micro and milli. If it's for voltage drop, micro and then milli, very, very small. The reason for which is it is for measuring small amounts of current and small amounts of potential difference between 2 points. Please, is it well understood? Human beings or beings? Oh, they are not talking now. We answer beings.
Human beings.
Human beings, like I said. Okay. So it's galvanometers have a very high internal resistance. And let's see if it has a very high internal resistance. Does that qualify it to be used as a galvanometer for measuring voltage and current? If it has a very high internal resistance, then meaning when you put into it current, it will always take small. So once it has a very high internal resistance, it will allow just small to bypass it. So it will certainly serve the purpose. If it is being used as for measuring small amount of voltage drop, then an ideal voltmeter must also have a very high internal resistance, even to the point that almost zero current flows through. And so it's having a very high internal resistance also satisfy the purpose for it's being used for small current. Is that okay? So its nature suits its function perfectly. Please, any question? Or if you want to contribute something, you are also allowed. So its nature fits its purpose perfectly. Sometimes we want to, if you want to use a galvanometer as an instrument for measuring current, ammeter or voltmeter, then it means that it must be worked on, because I'm designed to measure small currents. You want to use me to measure large currents. My inherent nature would not allow that. So if you are not ready to work on me, I will not be there to serve that purpose for you. Hence, the galvanometer must be adapted to be used as an ammeter or voltmeter. So we are going to look at converting a galvanometer as an ammeter and the other way around. So conversion of galvanometer to an ammeter. So this is a galvanometer G. We want to use this. A source of EMF is here. We have a galvanometer in a circuit. Okay, let me bring it here. A galvo here. We want to use this as an ammeter, because an ammeter measures large amount of current. Okay, so if current would always flow from the positive terminal, what it implies is that within the circuit, once this is there, it cannot even bypass the device, okay, for us to have a complete circuit. This is because the galvo has a very high internal resistance. So the best we can do is that, okay, let's create an alternative path. Let's create an alternative path so that within the circuit, if we could create something like this, when the current gets to this junction, it will break up into current coming here and another one coming here. But we must also incorporate into the circuit something with a very low internal resistance, because maximum current must actually come through this point and then go. Please, are you following the diagram? Current cannot move past this because it has a very high internal resistance. So what we want to do is that we want to create an alternate path. Okay, we want to use this to measure large current. So what is coming here is large. Because a galvanometer doesn't measure large, okay, amount of current. Two, that one effect is that when we allow the current to also pass through, it can damage the coil. It can damage the coil, because what is going into it is large. What is it measures is small. Okay, so one, the large amount of current can damage the galvanometer coil. Two, the large amount of current can also pass because it has a higher internal resistance. So the obvious way out is to create an alternative path. Now this path must have a very low internal resistance so that in effect we can always get a larger current within the circuit. So we connect a device with a very small internal resistance parallel to the galvanometer. So we connect a device with a very small internal resistance. And this device, whose internal resistance, very, very small, is known as shunt. So we say we connect a shunt, or we shunt the galvanometer. A shunt has a very small internal resistance, so that maximum current can always flow. So we create a path where the resistance is very, very low so that maximum current can always flow. So to convert a galvanometer to an ammeter, you connect a shunt, which is a device with a very small internal resistance parallel to the galvanometer. And small amounts of current will pass through this. So current going through the galvanometer, IG, and then current going through the shunt, IS. Now, when the two gets to this point, they'll all reunite. And what is coming to this end is the total current, okay, flowing through. And in doing so, you can always adapt this so that it will feed a larger example. If there is a load here that has to be powered, then by creating this, a larger or whatever is sent would come into this. So that is how we adapt a galvanometer to be used as an ammeter. Please, any question? How we adapt a galvanometer, okay, to be used as an ammeter, to connect a shunt, okay, across the galvanometer. And a shunt is a device with a very, very low internal resistance, so that larger amounts of current can pass through the shunt and then go to flow through, because the galvanometer will always block maximum current, or the maximum current can always damage the coil of the galvanometer. So we are left with the calculation. Okay, there is some calculation in here. Ishra?
Mr. Edia, so how does all you said, how does it convert the galvanometer to the how does it convert it to an ammeter? Because ain't it still the small currents that's going to be passing through the galvanometer?
No, you see, whatever we want to do is that this is a load. We want to feed this with a larger current, but this is a galvanometer. It's that if you don't do anything about it, the large amount of current you want to come here will not come, because by its nature, it takes small. So before you can let this take more, Israel, you must work on it, and that's the adaptation. Israel, you with me?
Yes, please.
So we are modifying this so that it will look like taking more. And so this is the modification. You connect a shunt in parallel, and the shunt must have a very low internal resistance so that larger currents can bypass it, bypass the galvanometer and pass through it. This will still take small though, but at the end of it, we'll have the larger chunk coming here because larger amounts will go through the shunt, smaller amounts will come through the galvanometer, but they will all come and meet at this junction and give us a larger amount of current, which is coming here. Israel, okay?
Yes, please.
So we are not actually looking at the small amounts passing through, but what is bypassing the whole arrangement? Because if we had used just this, it will not allow larger amounts. But we have adopted it or modified it so that large amounts of current can still go through the circuit. That's the whole thoughts behind it. Are you okay? And I mentioned, are you
Yes,
okay?
please.
All right.
Yes,
So
please.
we'll look at the calculation. Then we'll look at converting a galvanometer to a voltmeter. Then we start AC theory. As for Kirchhoff's law and potentiometer and Wheatstone bridge, meter bridge, we'll do it in school. Okay. So okay, I'll talk to you to see what we can also do about it. But some of you want to go for other classes. So please let's end here. And then I'll fix time so we continue tomorrow. Okay. Until then, take care of yourself. May God will be with you. And in fact, bye-bye.
Bye.